Welcome to this third video on thermochemistry. So in this lecture we will be discussing about Hess's law of constant heat summation of 4th semester thermodynamics portion. So it states that the standard reaction enthalpy is the sum of values for the individual reactions into which the overall reaction may be divided. Or you could also take down this very simple statements. If you go through once or twice, you'll be almost able to get the knack of that. The heat absorbed or evolved in a given chemical equation is the same whether the process occurs in one step or several steps. Okay, so why is this? I mean, where does this stem from? It This Hess's law of constant heat summation stems from the fact that enthalpy is a state function, meaning that it only depends on the initial and the final position, not on the journey that it goes through. Fine. So let us understand it numerically. There are two different methods of synthesizing sodium chloride. Sodium chloride is table salt NaCl made from sodium and chlorine. So two different methods of synthesizing. Sodium chloride. Okay, from sodium and chloride. So what is the method one? One is your sodium solid plus water liquid. You get sodium hydroxide plus half kg. The reaction enthalpy for this one is minus 140.87 kilojoules per mole. Now let me see if it is visible. Okay, I need to shift a little bit here. Okay, now this is and this half H hydrogen reacts with half chlorine to give you HCl gas. Now इसका delta, its reaction is minus 92.30 kilojoules per mole, and the last reaction you need to recreate, you need to create HCl in NaCl is HCl reacts with sodium hydroxide, NaCl. Okay, so what is the net change here? When you add all of them together, okay, so what all happens? Now this NaOH cancels with this NaOH, cancels with this, it cancels with water, water cancels with water. Now what you have is Na and half Cl2 HCl. Okay, this HCl gas also cancels with this. The net change is Na solid plus half Cl2 gas. So now to get this, all you need to do is add this one. I want to call this as step A, step B, and step C. Now if you add the enthalpy changes that are involved in each of these steps, so what you'll end up getting is minus 140.87 plus minus 92.3 plus minus 177.83. So you will get minus 411.0 kilojoules per mole. So this is the enthalpy of the whole reaction. Okay, just note down this value, very important, because we'll do by another method the same synthesis of sodium chloride and end up with the same value. That's the whole point. The whole point of Hess's law of constant heat summation is you go through any path, okay, the heat involved or evolved will be same, because essentially enthalpy is a state function. Okay, so this is your method 1. Let me take a new page here. What's the method 2? Reaction is minus 92 point, I mean this we have already seen previously. So what is the net change is, so if you add both of them, if I call this as step A in method 2, step B in method 2, and if I add both of this, okay, what I end up is 92.30. So we can calculate, you will end up with the same value that we calculated from the previous. So that is your delta H net reaction. Okay, so which means again the same thing, reiterating the same thing. H is a state function, and therefore you can add enthalpies around different paths. What you need is what is the initial point and the final point. Okay, so what are the consequences of, what are the applications of Hess's law? See, the whole point is you have state A, from state A you want to go to state B, okay, and there is some amount of heat that is involved here. Let me say that it is Q. Okay, now this is a single step. Now suppose you go through another point where you know C to D, and you take through three different steps: A to first C, and then C to D, and D to B. So Q1 is your heat involved in the heat change involved in step 1, Q2 is your step 2, and Q3 is your step 3. What you should be able to do is Q should and will always be equal to Q1 plus Q2 plus Q3. This is your simple statement of constant heat summation. So what are the applications of Hess's law? So first application, we'll discuss three applications, might come directly for your C3. So Hess's law makes it possible to calculate enthalpies of many reactions which cannot be determined experimentally. For example, it is extremely difficult to measure the heat evolved when carbon burns in oxygen to form carbon monoxide. It is difficult to calculate the enthalpy of reaction for the formation of carbon monoxide. So this particular reaction, so this is your carbon monoxide gas. Now, how we do this? If we want to calculate this, how we go about calculating this is, since we do not know this, let me say delta H carbon monoxide. Okay, reaction of carbon monoxide. So we use something that we know already, that is, combustion of heat evolved in combustion of 1 mole of carbon to give you carbon dioxide. So we know this. These values we know. Carbon, when it reacts with oxygen gas, it gives carbon dioxide. Okay, and the reaction, this reaction, carbon dioxide, the values we know is minus 393. 0.5 kilojoules per mole. Okay. Now, if I can do this the same thing in two different steps, if I can synthesize carbon dioxide in two different steps, how different is it going to be? It's going to be carbon first reacts with half of oxygen molecule to give carbon monoxide. Okay, this is something which I don't know. Then this carbon monoxide reacts with half O2 to give you carbon dioxide. Right, so I'll just put it this as oxide dash. Okay, now what this, from this thing we know, it is, this value is, suppose is minus 282.0 kilojoules per mole. Now how we can calculate this delta reaction, carbon dioxide should be equal to delta H reaction carbon monoxide plus reaction. Okay. Since we know this, we know this, and this can be calculated, and it is found out to be minus 111.5 kilojoules per mole. Okay, this is one application of Hess's law of constant heat summation. The second application, Hess's law, is useful in determination of enthalpies of, in determination of slow reactions. Now, one of the slow reaction is, transformation of rhombic sulfur into monoclinic. Now this calculation is, direct measurement of enthalpy is not possible for this. It is very slow. So direct measurement is not possible. So what do we do? What we know is enthalpies of combustion of rhombic sulfur and monoclinic sulfur. Both are solid forms of sulfur. So we know combustion of rhombic sulfur, and this delta H value is minus 297.5 kilojoules per mole, and we also know the combustion of monoclinic sulfur. Now, how do we get from rhombic sulfur to monoclinic sulfurs? So simply we subtract 1 from 2, so you get monoclinic to rhombic. Your delta H is minus 2.5 kilojoules. Okay. Or if you rhombic to monoclinic, delta H values plus 2.5. Okay, so what it means is transformation sulfur is accompanied by absorption of 2.5 kilojoules of heat. The third application is calculation of enthalpies of formation. So enthalpies of formation of those reactions where it is not possible to determine these experimentally. When it is not possible to determine these experimentally. One very simple example is, we cannot determine experimentally the enthalpy of formation of benzene from its element carbon and hydrogen. It is not possible. So what we know is the enthalpy of combustion of benzene and enthalpies of formation of water and carbon dioxide. The data that we know is C6H6. The combustion of carbon, which is to give carbon dioxide. This is your kilojoules. Now, how do we go about calculating the enthalpy of formation of carbon benzene is? So this equation, if we multiply by 6, okay, and is multiplied by 3. Now your 4 is 6 carbon plus 6 oxygen, so it will give 6 carbon dioxide, and your delta H is going to be 6 times of this particular, so it's going to be minus 2361 kilojoules, and your so if you multiply this by 3 times, it's going to be minus 857.7 kilojoules. So if we add 4 and 5 and subtract 1, what do we get is 6 carbon solid plus 3H2 gas reacts to give C6H6. See, this is not experimentally how benzene is formed, okay, in lab conditions. Okay, this is just your predict. We are just trying to predict the enthalpy of formation. That's all. So this, if you do this, you will get kilojoules, which means enthalpy of formation of benzene is 49.0 kilojoules. Okay, so now let us do a small numerical based on Hess's law of constant heat summation. The question is the standard reaction enthalpy for the hydrogenation of propene CH2 double bond CH3 is given to be 124 kilojoules per mole. The standard reaction enthalpy for the combustion of propane is minus 2220 kilojoules per mole, and the standard reaction enthalpy for the formation of water is 286 kilojoules per mole. Now the question is, calculate the standard enthalpy of combustion of propene. So this is like, you have to get a knack of solving such numericals. इसमें कुछ भी concept नहीं है. This is like SSC CGL. If you have written those exams, if 5 apples cost how much, 10 bananas will cost this much, and calculate the 1 apple ka banana ka. So the whole these numericals are like that. So with practice you'll be able to get the knack of this. Starting it will seem non-intuitive. Okay, it is not linear. Okay, these numerical problems are not linear, so you have to have little bit of intuition to be able to get the correct answer. I use the wrong word. You have to have some intuition for this. Okay, it comes with practice. You can develop it with practice. So what is the combustion of propene? So the formula of propene is C3H6 gas plus 9/2 water, again gas. This is carbon dioxide plus 2 is water. Fine. This equation, this reaction can be recreated using C3H6 gas plus H2 I'm just putting it kilojoules per mole. Okay, the next I'm just going to enter the values here, which is minus 124. Okay, and the combustion of propane is the value is minus 2220, and decomposition of water to H2 gas plus half water. So this is plus 286. Note down the values. Okay. What is the net change here? Net change is C3H6 gas plus. So how much oxygen? 5 oxygen minus half oxygen, which is 9/2 oxygen. This is 3 carbon dioxide gas plus 3 water. Okay, the value that you are going to get is minus 2058 kilojoules per mole. Okay, so this is your combustion of propane. Okay, so thank you for this. See you. Bye bye.